to our CCPO-ICAR seminar and continuing our awesome set of speakers this semester. Today, my pleasure to introduce Dr. Tony Rodriguez from UNC. So he's going to talk to us today about his most recent work looking at oysters, sea level rise, and some of the natural and nature-based features and benefits that they provide. Tony has a bachelor's from Hamilton College and a PhD from Rice University, and has been there at UNC for several years, most of his postdoc career. So take it away, Tony, and if you have questions, folks, we'll save them for the end, but you're welcome to put some in the chat if you want to get in kind of in the queue.
So yeah, I want to talk about intertidal oyster reef growth, resilience to sea level rise, and their place in nature-based infrastructure designs. And I really had a lot of fun putting this talk together. I've never given a talk on this topic for longer than 15 minutes at a meeting. So it was really nice to put it all together in kind of a longer format. So before I begin, I definitely want to acknowledge some people and funding agencies, and you're going to see some of these projects were just a tremendous amount of work, and there's so many people that you need to thank that aren't on this slide. So we had teams of undergraduate students, graduate students, and technicians who worked on this project, but I just wanted to highlight a few people. Justin Ridge, he's one of my former PhD students, and he worked on a lot of the projects I'm going to be presenting today. Molly Bost, who's defending in just a few weeks. I'm going to talk about one of her chapters of her dissertation. All of this work was done. I've been working on oyster reefs for maybe the last 12 years, which some of you might think is really long, and others, I've just started. But all of this work was done with Joel Fodry, and he's an ecologist. So we have a nice team there, a geologist and an ecologist working together. And then Carson Miller is a master's student who worked on a lot of this work with us. And Ethan Tierkoff also helped from the beginning. Let me see if I can get laser pointer. No. Okay. So this is a figure that Joel Fodry put together, and what we're looking at here in blue are North Carolina landings in pounds of meat per year from the late 1800s to close to present. And you can see it's just declined through time as the value of oysters have gone up with supply and demand. And this is really a common story of oysters being overfished in estuaries. So I've seen a very similar figure for Chesapeake Sound. So oysters are really on the decline. And today I'm going to be talking about intertidal oyster reefs. Most of what we eat and fish are subtidal oyster reefs. And if we look at the difference here, they have really different morphology. So these are subtidal oysters, what you would get at an oyster bar. Intertidal oysters are much longer, elongated, thin-shelled, really sharp. This is all Chrysostrea virginica, so same species. So continuing on in that vein, this is from Noaa. Oyster populations are at historic lows, and they mainly attribute this to development, wetland loss, excessive nutrient pollution, diseases, overfishing, and outdating harvest methods. So this isn't a North Carolina problem. It's, Beck et al. In 2011 estimated that 85% of oyster reefs have been lost globally. So oysters have just been on the decline everywhere, and restoration in the intertidal is becoming really popular. And so if we look at, again, this is from Noaa, and we're looking at coastal structures from hard techniques like bulkheads and revetments to all the way on the left, we've got, nature-based techniques, replanting salt marsh. In the southeast, we don't have any rock along our shores. Only the hard substrate we have are oyster reefs. So restoring oyster reefs in front of a salt marsh somewhere here in the scheme, this is where maybe gray-green infrastructure would be. The oyster reef would serve as a breakwater and start protecting upland and maybe developments from wave action during storms. And so there's been a huge emphasis in this right now. And these are just some highlights. I really like this quote from the Washington Post: "This New York storm barrier could have slowed down Hurricane Sandy, but European settlers ate it." So they've got the $1 billion oyster project in New York. And so after Hurricane Sandy, there was a lot of talk that it wouldn't have been so bad for New York if we hadn't ruined our oyster reefs. And it's the same in the Gulf Coast. They have $38.5 million from Deepwater Horizon payouts that have been going towards restoring oyster reefs. And these are mainly intertidal restoration projects and really large ones. So, what do these restoration projects look like? We had one at the Institute of Marine Sciences, and this is what our shoreline looked like before the restoration project. And, so many of the folks at IMS are studying nature-based solutions to shoreline resistance from storms and resilience. And we have a terrible shoreline. It's a riprap shoreline. So we went out and constructed an oyster reef sill, and this took about a week. And this is just a time-lapse movie of us doing this. We would load oyster shell on this small boat and just kind of dump it in this configuration that we had planned out ahead of time and have it marked with those PVC poles. So these are, pretty time consuming. They can be expensive projects. This one wasn't, because all of our labor was free. We just had to buy the oyster shell. And we were really targeting a specific elevation. So you'll see in a moment, after we dump all of the shell, we're going to come out here with rakes in just a moment and start raking that shell into a particular configuration. You can see we've got two sills here. And our big problem is the intercoastal waterway is in the background. And so we have large ships that come by and they kick up large wakes. And that's why we have trouble growing salt marsh. And you can see right in the foreground, we planted some salt marsh and we see those little sprigs. And so if we look at aerial view, this was done in around 2014. This is before we put the oyster shell out. And of course, maybe 2 weeks after we put all that oyster shell out, we had a hurricane. And you can see that shell's already started to move landward because it didn't have a chance for new spat to colonize and grow and kind of hold it together. And so here are in December, and you can see that landward movement of it, not much salt marsh. Now the salt marsh is starting to come in. You can see we've got a little patch over here on the left side of the dock. And in 2019, this is my last time step. Now the salt marsh has really started to bloom, I guess. And what's the longevity of this project? Was it a success or a failure? I think short term it was a success. We do have this breakwater out here, but if you're on the ground, there are really not that many living oysters. We have this nice salt marsh that's still expanding. But moving forward, how long is this project going to be around for? And I would argue not that long, because this shell, never was colonized by oysters, and it's just going to continue to move around and provide less wave dampening action. And this will eventually be eroded away, unfortunately. So I would say, one of the most important indicators of oyster reef restoration success needs to be reef growth. if the reef isn't growing, you have a pile of shell out there, and it's providing some services, fish habitat, it's doing some good things. But eventually, it's with sea level rise, it'll just become buried, and it might start looking like this, as opposed to a vibrant reef with growing oysters. So there's, in the intertidal regime, there's a niche where oysters really grow the best. And this is some work from Melanie Bishop and Pete Peterson at IMS that they published in 2006. And what they did is they put individual oysters on these on tables at different elevations within the tidal regime. And what they found was that this was a 6-month period study, so a really short study. So even within that 6 months, the oyster shells, or the live oysters that were placed higher up in the intertidal, started to surpass the oysters that were placed lower. And I'm talking about in terms of growth. And it's because those subtidal oysters, this is the high salinity parts of estuaries, they received a lot of fouling from things like boring sponge and barnacles and bryozoans. And that started to hamper their growth. They were being outcompeted. So there's this model, oysters require these niches to live, and in the upper estuary, the niche is low salinity water. And that's typically, sorry about that, that's typically where they occupy subtidal regions, because they do better when they're underwater all the time. And they can outcompete other organisms because they can withstand low salinity waters. Now, down here in the estuary, where we have much saltier water, their niche is the intertidal. And so they need to be exposed for a period of time, or that's when the reef looks like this if it's too low, and it just gets outcompeted with things like barnacles and boring sponge. And carrying on from that earlier study with Pete Peterson and Melanie Bishop, we went out and we tried to scale that up, and we constructed large reefs. So these are experimental reefs, and smaller versions of them. So 9 by 7 meters, 5 by 3 meters. And we did this at 4 different elevations. So down here, let's see if I can move everyone over. So down here, these lower elevations are almost subtidal reefs. And over a 12-month period, that's what this time step is showing. You can see we have no reef growth when it was low. And when you're up higher in the tidal range, these reefs did really well. And here's the on the ground view. And you can see all these new live oysters just after 12 months. And these oysters that were grown lower, you can see all of the organisms that have outcompeted them. So in our work, we've tried to put oyster reef growth in this pretty well-known conceptual model for carbonate depositional environments. And the way this model works is for carbonate systems, you need to have space between the substrate and sea level for the reef to grow. And so when there's a lot of space, they kind of catch up to sea level and they accrete really rapidly. And so we call that the catch-up phase. And that's what this reef is experiencing from time 0 up to time 2 here. And then once they reach that upper limit, then they're really confined to sea level, and they're in that keep-up phase. So they just start growing with sea level rise. And eventually something could happen to conditions. Maybe we have sediment loading or something, and they're in the give up phase and they get completely buried in sediment. It could be that the rate of sea level rise starts exceeding their growth rate. or it could be some other environmental parameter. And so if we apply that model to oyster reefs, this is a seismic line from Corpus Christi Bay in Texas. And so what you're seeing here is here's depth on the y-axis, and here's distance. This is water column up here. This is kind of old seismic data. This is the bay floor. So that's about 2.5 meters deep at this location. And what you're seeing is an oyster reef right here, and eventually it becomes buried in marine mud. And as the reef is growing, you can see, not marine mud, but estuarine mud. You can see the estuarine mud kind of keeping up, and as the reef grows, it starts to bury the flanks. And if we put some interpretation on this, I think what's happening with this reef, and we haven't sampled it, and so this is all, pie in the sky. I think we have this catch-up phase where we have rapid vertical growth. And then we have this keep up phase. It reaches sea level and it starts growing out laterally, because that's where there's space that's below sea level. And then eventually conditions changed. Maybe it was a salinity thing, and it gives up and becomes buried in estuarine sediment. So with all this emphasis on intertidal oysters and restoring them along shorelines to help prevent erosion. And hopefully I convinced you, you really need to have that reef to grow in order to provide that service through time. So we wanted to shift away from studying individual oysters on reefs to studying the whole reef itself. How does it grow? How does it evolve through time? Does it fit into that carbonate depositional system model that I just presented? And so some of the research questions I'm going to be addressing, I'm going to get into the data in just a second. So how fast can reefs grow? What intertidal areas maximize growth rates? So that's important. We want to target those intertidal areas when we're restoring reefs. And how resilient are oyster reefs to changes in sea level? And how can we best integrate oyster reefs in living shoreline designs that optimize their potential for growth? And some of these pictures up above, I mean, you can see this oyster reef, it's really high. It's even higher elevation than the salt marsh. I'm not sure that's going to be growing through time. This one's a little bit lower. Here's a really successful restoration project with a vibrant salt marsh behind it. And so this is oyster reef in the foreground that Noaa put together. This is Noaa on Pivers Island, right near where I live in North Carolina. So the types of reefs we've been studying are those experimental restored reefs. So these are piles of shell, culch, that are sculpted into rectangles that are about 15 centimeters high when we first put them out. And then we kind of track how they grow through time. So that's one part of the data set. And then we look at natural reefs too. And natural intertidal reefs have really two configurations, and one of them is a fringing reef. And this is just a classic example of a natural shoreline transition where we have subtidal with seagrass, and then here's our oyster reef, and it's fringing salt marsh up here. And if we were to continue this photo to the left, you'd see upland forest. And then the other type of natural reef, intertidal reef that we're looking at are these patch reefs. And these grow just on their own in the middle of estuaries. Here's a large patch reef in the foreground, and you can see there's some salt marsh colonization. This image is from the Shallot River estuary. And I'm going to talk about that at the end of the talk. And you can see there are lots of patch reefs out here in the Shallot River estuary in the background even. Okay, so the first question, how fast can reefs grow? Before I do that, I just want to talk a little bit about some terminology. So here's my model of an oyster reef. And an oyster reef has this kind of outer rind to it in gray. And that's where we have living oysters and lots of pore space in between those oysters as they grow on top of one another. And we call this the taphonomically active zone. And that's transition from living oysters growing on top of one another to dead oysters that are getting buried in the reef core, which is composed of dead oysters and lots of sand, silt, and clay, mostly silt and clay. And if you look at the literature before we started this work, that's mostly based on looking at historical bathymetric maps and just a few cores that might have radiocarbon dates, how fast do reefs grow, and those papers would indicate about 0.5 centimeter per year are those reported values. So we wanted to test that, and so we went out, and this part of the project really looks at those experimental reefs. And experimental reefs in our area, so here's Cape Lookout, Beaufort Inlet, Shackelford Banks, and this area here, Middlemarsh. So all these experimental reefs were constructed in Middlemarsh, and some were constructed in 1997, others in 2000, and we had 6 reefs that we constructed in 2011. And so the first thing we did is we used this coring device. Really, it's a jackhammer hooked to an aluminum piece of pipe, and the jackhammer pounds the pipe into the top of the reefs. And because we know when the reef was restored at the bottom, so we've got a time there, and we know when we collected the core, so we have that time period, and then we can take the thickness of the reef and just divide, and that can give us an accumulation rate, or how rapidly that reef grew. And so here are some from 1997, and you can see this is a thick reef. This one from 2000 is a little bit thinner. Here's that taphonomically active zone on top, and here's the reef core. And overall, what the cores told us is that the reef growth rate is about 2.7 centimeters per year. So quite a bit higher than those older estimates based on maps and radiocarbon dates. I mean, that's still an astounding rate of growth, I think. And if you look at more details of the cores, so we took those cores and we split them every 5 centimeters, and we would wash the material and measure how much sediment we had, how much shell. And remember, these are restored reefs, and we restored those reefs with subtidal shells, which was good. So we can really recognize this is the culch material. So we don't count these intervals for reef growth. And then as you move up core, you start getting this intertidal shell morphology. And so this is all new growth. So the cores were interesting, but they tell you reef growth on top of the reef, just on their crest and at that one location. And we really wanted to see, well, first of all, that rate of growth is unsustainable, right? You can't, the rate of sea level rise is about 3 millimeters per year. And if the reef is growing constantly, even at 2.7 centimeters per year, it's eventually going to reach that growth ceiling. So we really haven't done a great job. That should be a lower estimate of reef growth. So we decided to try a different approach, and we had this terrestrial laser scanner, and we wanted to know if we could scan the reefs over a practical time period, so maybe 1 or 2 years, if we'd be able to measure growth with this device directly. So the first thing we did is we went behind the building and we constructed a fake oyster reef on a piece of plywood, and we scanned it. And we scanned it 3 times, and we had these reflectors within the scan area, and that's how we geoposition the reef. And so we need to know whether we can scan this reef and get it in the same spot each time, so that when we subtract those topography maps from one another and measure growth, that's accurate and precise. So this is what we found. So here's our pile of shell on the grass, and we just looked at the middle of the shell mass, and that's what's clipped out here. So these are digital elevation models, And we're a little bit below individual shells, being able to image individual shells, but we can image clusters. And if we subtract these maps from each other, we get these subtraction maps. And so blue is where one map was above the other map, and red is where it's below. And we take all of these grid cells and we can plot them up, and the mean is just about 0, which is really good. That means that the data is not biased. It's not always a little bit lower than it should be. And if we take the standard deviation, we're looking at maybe a resolution of 1.5 centimeters per year. So this method should work well, because reefs grow faster than maybe 3 centimeters a year. So that should be within the realm of possibilities with this tool. And this is what some of the data look like. Let's see if I can. This is supposed to be a movie. But anyway, we can skip the movie, but we would be, oh boy. Let me move you guys over. Bear with me. No, doesn't want to play. Well, if it did play, we'd kind of zoom in on the reef, and we'd see the point cloud and everything out here are, this is us in scanning. So we need to move that scanner around the reef in a few different locations, and then stitch all those point clouds together and come up with a digital elevation model of the reef. And, that was maybe 10 years ago, 9 years ago, and that's all obsolete technology now. So we've been messing around with drones, and drones do just as good of a job as that terrestrial laser scanner does. And here's an image. We did the same experiment. We flew the same reef 3 times, and we created digital elevation models, and we had a bunch of checkpoints on the ground. And the error with using structure from motion from images is about the same as the terrestrial laser scanner, but you have the benefit of being able to map a larger area in a shorter period of time. That movie I just showed you, the point cloud, that didn't work. That took all day to map that reef, and we would have been able to do it with a drone in probably 15 minutes. And here's, the same maps, but a little bit different color. These are the subtraction maps, and what we're seeing with error. And so the standard deviation we're looking at, less than 2 centimeters error with drone data. But unfortunately, everything I'm going to be talking about today is with the terrestrial laser scanner. Okay, so let's look at some of those results. And this is just a reminder that that 2.7 centimeters per year that we measured from the cores is really a minimum estimate. And so we went out, and this is one of those restored reefs that was restored in 2011. And this is what it looked like 0.1 years after we put the cult shell out. So you can see that rectangular shape. And now we're switching to digital elevation models. So in red, that's high elevation, and blue is low elevation. And so almost a year, this is what the topography of the reef looks like. And you can see the morphology of the reef has really changed. And then after 1.75 years, we have a lot more red on top. And so you can subtract these 2 maps. And that's what we're seeing with blue as positive. And that whole reef surface has increased. Here's the scale. So the darkest blue is 20 centimeters. If we look at an older reef, here's the first scan. This is one of those reefs that was restored in 1997. So about 10 years after it was restored, this is the digital elevation model. And then a couple years after that, you can see that the redder areas or the higher elevations is along the sides of the reef. And if we take the subtraction map, and that's what's shown here, the top of the reef wasn't growing at all. And we have areas of erosion. You can see these dots. This is where we collected cores. This is this feature on the reef, and that's just a boat prop impacting the reef. So we picked that up, but it didn't grow on top anymore during that time step. The maximum growth is really along the sides of the reef. So the top of the reef hit that growth ceiling, and then it started to expand laterally. So if we put that together, what I'm showing you here is topographic profiles across these experimental reefs. And so this here, so we've got distance, elevation. This is the culch material that was planted in that rectangular position. And now we're looking at various years. So here's the first time step, the second time step, the third, the fourth, and these are different reefs too. So, you know, a little bit of, this isn't the same reef. So it's a compilation of data. But what it's showing is that vertical growth. So this would be kind of that catch-up phase. So there's a lot of space between where the culch was planted and sea level, and the reef grew vertically really rapidly. And then we have that keep-up phase, and that's where growth, it starts to grow laterally along its sides, because that's where the space is that it can grow in the intertidal. So if we just look at vertical accretion and we look at this regression line, the maximum growth rate we measured, it suggests it's about 10 or 11 centimeters per year. So much faster than what we could see from the cores. And the reason it's growing so rapidly is that the oysters are growing on top of each other. So that growth rate of an individual oyster, when you have 3 stacked on top of each other, is really additive. And that's how you get these rapid rates. It's the clusters that are doing it. And from this work, we also found that the restored reefs double in area and volume every 9.5 and 4 years, respectively. So they're really doing well in terms of growth. So based on those experimental reefs, you know, what intertidal areas maximize growth rates? We also had water level loggers out at the same time. I should have mentioned that. So we can convert from elevation to how often the reef is exposed to air. And so we were finding that this, so here's the kind of a growth curve moving from the top of the reef down to the bottom. And if the shell's too low, you know, we're approaching subtidal, and that's where it gets outcompeted. So we have low growth right near the substrate. And then as we move into this 20 to 40% time that the shell's exposed to air, that's where we're finding the highest growth rates. And then you move up the reef on the reef crest, then growth rates move down to about the rate of sea level rise. And so we call that the growth ceiling. Okay, so we're gonna go back to that model in just a second, but I wanna shift gears a little bit and talk about how resilient are oyster reefs to changes in sea level. And again, it's the same study area. So we're looking at this region, mostly middle marsh. So again, here's Cape Lookout. We wanted to include those young experimental reefs, those older kind of decadal experimental reefs, and we wanted to include a natural reef, and we only have one natural reef in this study, and it's this one right here, and this is what the image looks like, which was the title slide. And so that natural reef, we kind of need to shift away from just experimental reefs and start looking at natural reef growth. And this is what one of the topography maps looks like. It's difficult to map natural reefs with this technique because you can only map one reef in one day, because remember, we have to map at low tide. So what we did is we looked at periods that we could scan the reef and what sea level was doing. And we grouped the data into these two periods. And one is where sea level is generally below what it was predicted to be. So this is kind of our low sea level scenario. And then we have this other period where we have lots of sea level anomalies in the area. And those are mainly linked to wind direction and mostly the velocity of the Gulf Stream that impacts water level in our area of the coast and other areas too. So we had a couple of years with frequent sea level anomalies. So the average sea level was higher. And we wanted to see, how did the oyster reefs respond to these changes in short-term sea level, which should be an indicator of how resilient they are to sea level rise. So if we look at the decade-old reefs, this figure is pertaining to this particular reef. The name of it's not important. Up here is this topographic cross-section or profile across the reef. And the first time we scanned it was in 2010, and that's shown in white. So here's distance and here's elevation. And this figure is showing how much the reef grew. So the growth rate down here, so vertical accretion in centimeters per year at every elevation along the reef. So this curve is based on points that are binned about every 2 centimeters and represent hundreds to thousands of observations from the digital elevation model subtractions on the reef. And I'm just representing this in 2D up here. So this curve represents the elevations where we had the most growth here between the white and red scan. So between 2010 and 2012, when sea level was here. And this is just denoting where that optimal growth zone is. And so if I click down to the next slide, this is during those sea level anomalies. And we predicted that the optimal growth zone would increase, and it did. So it moved up on the reef with just this small change in sea level rise. So now the optimal growth zone has shifted up to compensate for that extra space. And it responded within that 2-year period. And if we look at the natural reef, this natural reef's been around for a while. We cored it and radiocarbon dated the first oyster to colonize this area, and that was about 1746 AD. So this has been around for a while, and this reef responded very similarly. So here's the profile, or here's the growth curve, and here's the profile off part of the reef. And you can see we had very little growth during this first time period. Oops. But we look at the period of sea level anomalies, and the reef really kicked on, and that optimal growth zone increased in elevation, within the resolution of our data. So this suggests that reefs respond, or their growth responds, within a year or shorter to changes in sea level. So not only can they keep up with any rate of sea level rise, as the rate of sea level rise accelerates, they respond immediately. Okay, and I don't know if you looked at our funding. On that first slide, I should have mentioned, it's all kind of North Carolina funding based. And that's not by design. We've tried to get money elsewhere, but we've really been stuck in North Carolina looking at reef growth. And we need to move away to different systems. And we've been focused on these restored reefs, and we need to look at natural reefs. But that's the funding game. So we haven't been able to move out of North Carolina yet. But with this last project, we have been able to increase our range a little bit. So we wanted to kind of revisit this model. This really based on those experimental reefs and see if it applies to natural reefs, and natural reefs in different landscape settings, so patch reefs and fringing reefs, and in different tidal regimes. And so southern North Carolina, the tidal range is higher than it is in Back Sound. So we can set up this nice comparison. And so that's, this is really the final research project I'm going to talk about. And I know I'm going over time, so I better speed up. So here we go. Back Sound, we have a tidal range of about 1 meter. We went to Shallotte down here, where the tidal range is about 1.5 meters. And in each of these estuaries, we looked at 3 fringing reefs and 3 patch reefs. And all of those reefs are natural. And we cored each one of those reefs. And we wanted to find out how old the reef was. And we dated material, the first oyster to colonize the area. So we have a nice time series. These are digital elevation models of all the reefs and profiles across them. And what I want to point out, so the Shallotte River estuary, higher tidal range, and those reefs extend to lower elevations, and these are patch reefs. And the fringing reefs in Shallotte also extend to lower elevations. So we had water level loggers out too at both of those sites. And if we look at the water level logger data, we can convert elevation to aerial exposure. And remember, we predicted that 40 to 20% aerial exposure, that's that optimal growth zone. Well, if you look at Shallotte with the larger tidal range, those elevations are lower than Back Sound. And so we've got this conceptual model that we wanted to test. So in the larger tidal range, the optimal growth zone should be lower, and these reefs should extend to lower elevations too, like I just showed you on the previous slide. And the results really show that. So this is the median growth across a time step at all of these elevations. So you can see for Back Sound, the optimal growth zone is higher than it is in Shallotte River estuary, like that model predicts. And that's true whether you're looking at patch reefs up here or fringing reefs down here. So what we weren't expecting to find is that that 20 to 40% optimal growth zone for aerial exposure really didn't hold to be true. And we weren't expecting that the aerial exposures for the reefs in the Shallotte River estuary to be so much lower than the natural reefs in Bogue Sound. So what I've plotted here, this circle, that's the aerial exposure of where these reefs grew most rapidly. And the bar up here is the elevation or the aerial exposure at the reef crest. And we plotted this against the date of reef formation just to separate them out. And you can see all these reefs in the Shallotte River estuary are actually lower in the tidal frame than Bogue Sound. And all of the reefs are higher than what we would have predicted from that growth model that was based on the experimental reefs. And we really think temperature is playing a big role here. So in Shallotte, it's further south, much warmer temperatures. And the reefs are responding to that by staying a little bit lower in the water where they're underwater more often so that they can not dry out entirely. We still need to do some work here to verify this further. Okay, so some conclusions. Oyster reefs can grow really rapidly, about 11 centimeters per year until they reach their growth ceiling. What that means is they should be able to keep up with any rate of sea level rise that's predicted. And they're also really resilient to short-term increases in the rate of sea level rise. And here's just that natural reef that didn't grow much at all and even showed a lot of erosion during that first time step. And then during the sea level anomalies, growth really turned on, and you can see we've shifted to growth across the entire reef platform. if we just look at a time series of reefs in back sound, down here, these are, so the size of the circle is the growth rate. And this is where we have the maximum growth rate with percent aerial exposure. And so these are all those experimental reefs where we have the maximum growth rate, low between 20 and 40% aerial exposure. And you can see that climb until the reef becomes about 50 years old. And then, we're all the way up here where we have the maximum growth of about at 50 to 60% aerial exposure. So they're really, this model of optimal growth zone changes as the reef matures. And other factors like temperature also influence where you should be restoring reefs in the intertidal realm. Okay, and I know I zoomed through the conclusions, but I wanted to get to this slide with final thoughts. So where are we going? We're restoring reefs in this Sill configuration, like we did at the Institute of Marine Sciences, where the reef is parallel to shore, like a breakwater. And in nature, they don't grow this way. Oyster reefs that are fringing salt marsh, they grow like groins because they want to maximize the flow over the reef this way. And we've known this for a while. This is a 1901 publication where a grave illustrates these oyster reef groins in their natural configuration. And so some of our new research that's coming online is maybe to try this kind of groin configuration. And maybe we're approaching this nature-based infrastructure a little bit wrong. If we want to maximize growth, maybe we should consider planting shell in a configuration that's perpendicular to shore instead of parallel. All right, and that's my last slide.
Oh, thanks, Tony. I'll hold the applause, but a lot of spatial thinking as a geographer, you got it from me. But we have a couple minutes for some questions from the audience. If you want to either raise your hand or drop a question in the chat, welcome that. I know we had one question, and you were using a terrestrial laser scanner, I think, for most of that analysis. But it looks like you said drone technologies really right up there now, so you could enable that.
Yeah.
How about John? You got a question?
Yeah. Hi, Tony. Thanks. I was curious if you're getting sort of confusing effects due to the salinity and temperature changes while this sea level is going on. I did notice there were slight differences in temperature and salinity in the two cases you mentioned. And so is that important at all, or is really the height the big player?
No, I mean, I think it could definitely be important. I don't think it was in those time periods, but like that Corpus Christi example that I showed of seismic data, people have hypothesized that what the demise of, that's just one example of a whole bunch of intertidal reefs that became buried. People hypothesized that it was a shift in salinity that caused that. So, I mean, I think what you're saying is right on, like salinity is really important. And it's, reconfiguring inlets in North Carolina, that could really shift things around.
Yeah, I mean, it also plays into the various diseases, dermo and all that sort of stuff. So it's a little bit unclear to me that with the modern expansion of these diseases compared to, 100 years ago, is there some danger in comparing these old relic reefs with some of the newer forms? Anyway, just sort of what's your take on the modern disease expansion versus older times when it was less diseased?
Yeah, I mean,
maybe an unfair question.
Maybe unfair.
Right now. Yeah, I don't know. Maybe. Yeah, go ahead.
No, I mean, I don't know either.
Yeah, I just thought I'd poke you a little bit and see what you say. So anyway, thank you very much.
Thanks, John.
I see a question or two in the chat. So Charmaine asks, which of are really informing actual restoration efforts? You alluded to that at the end there, that maybe we need to rethink the morphology. As a lot of people see the erosion control kind of aspects, maybe that was the underlying part of your original design. But the perpendicular shape. Is this translate to actual design implications?
Yeah, I'm hoping so. So the first thing we need to do is look at these different configurations, and I'm not 100% convinced. So when we see that groin, is that because the oyster reef grew out, or is it because the salt marsh eroded back? And that's the first thing we need to test. And that's what we're trying to do with this project. And then maybe the second step, whatever we find there, then maybe we can make a recommendation. Let's try restoring in these new configurations.
Yeah, well, I guess a lot of variables historically versus now.
Yeah.
And Gannon there asks about any ethical concerns with using oysters in restoration.
Well, one ethical concern, which we already have to address, is, are we replacing one habitat for another, and, valuing some ecosystem services over others? And that pertains with if we have seagrass in the area mostly. So, we can't do this in any area that would impact seagrass or another really valuable habitat. But I think I might be missing something. So, like, what other ethical concerns?
I don't know. Now, Gannon, you can chime in if you care to. But yeah, I mean, like, you could be preferring oysters to something else, or now you're using in that case, you had oyster shells from a seafood restaurant or something, right? Or donated.
Yeah, I guess another ethical concern could be, are we putting them in plastic bags? And, that's a really common way of restoring reefs. And so now we're introducing all this plastic. And we haven't done that, but others have had, great luck restoring reefs that way. We have someone at IMS who has this new oyster catcher substrate, which is this concrete product, and it's all natural, and it's supposed to degrade naturally once the reef takes off. And that's a really nice and very popular alternative.
There's another one. Do any of the local oyster harvesters help with your studies? Or have they voiced any concern, pro or con?
Yeah, they've been, when we started restoring these reefs, they were partners in a lot of this. So we were doing a lot of the restoration when they weren't fishing. And so we would hire them to help restore reefs. And sometimes the reefs were doing so well, we had signs up saying that they were sanctuaries, but you would see fishermen out there taking oysters from them. And, that could really influence our maps.
Well, and I mean, there's co-benefits of them, like you've talked about many. I had a collision with an oyster reef one time, and it left me quite damaged. I thought it was a seagrass bed, and I was gonna ride right over it. Confession, I was on a windsurfer, and instead I flipped over the handlebars and landed in, flat-faced on the oyster reef.
Oh my gosh.
Yeah, it's pretty terrible.
Did you go to the hospital?
No, but I was concerned about, talking about diseases, Vibrio
yes.
and a number of other things. It's actually kind of hazardous work. I know if you have anything to say about that, I mean, we don't have as many up here, of course, anymore. It's a very similar situation to the loss of decline of reefs.
Yeah, I mean, I've had lots of people injured on oyster reefs, for sure, but we try and minimize that.
Yeah.
So Tony, if you have just a moment, there's been a lot of focus on using oysters as a way to restore reefs and restore ecosystems. Are there other organisms that could do that, that would survive in the North Carolina or Virginia sounds? I mean, clearly coral won't, and putting a bunch of clams out isn't going to do anything. They don't build reefs. And so I'm wondering if there's something else, some other organism that might be as useful as oysters, which everyone wants to take for consumption. So something that humans don't eat that wouldn't build a reef.
I can't think of anything that would be natural. We might be able to introduce some species, but
Yeah, introducing is always kind of, you know, a triple-edged thing because we always screw up and go, oh, nothing's going to bother with this. And, you know, then you have the kudzu thing where, you know, it takes over the world. So anyway,
Yeah,
I'm just curious if there are any other thoughts of other organisms.
no, I can't think of any.
Yeah.
I think I'd heard of some ideas to introduce Asian oysters. You know, they sterilize them and introduce them. But, you know, I always refer my students to the Jurassic Park. You know, nature finds a way. I don't know if that was ever got serious. But,
Yeah, they have a different salinity tolerance, if I'm remembering back, and so they like it a little fresher. Maybe Eileen can correct my bad biology, but they talked about it. Actually, they weren't really sterilized. Some people said they still were able, I think they were triploid or something. Anyway, they were still able to reproduce a bit, but they couldn't grow. Maybe someone can correct my inappropriate biology.
They did try Asian oysters about 20 years ago, but they're a low turbidity animal. And Chesapeake Bay's turbidity levels, that's the problem with introducing something like Chrysostiogygus. They're in low turbidity environments. So.
oh. Something we have an issue with. Sure.
So if we could just get some Virginica to clean everything up, then we can get the Gygus to grow, you know, compounding everything. Anyway, sorry.
Well, I think we're close to time. Any final question? No, seeing none. Let's thank you again, Tony, for an extremely interesting talk. I hope you can continue this line of research and expand it north, south, elsewhere. Super
Thanks so much.
interesting.
Thanks for having me.
Excellent. And thanks everyone for joining.